So exactly as Jean-Louis said, I will discuss here multidimensional continued fractions. There is a huge variety of multidimensional continued fractions, but I will focus on the ones who have an underlying dynamical structure, and in particular on continued fractions generated by matrices, matricial continued fractions. But before entering into the vast zoology of continued fractions, I will start by recalling facts on usual continued fractions. So I've got the feeling that the main part of this lecture will be devoted to the usual regular case. It will help us later to go faster when we will go to higher dimensions. So just to start with, who has never heard of continued fractions? Okay, thank you, Sebastian. Cool. So then I can feel comfortable. So the idea is to represent numbers under this form, as you know. Well, I stop here. And I can have maybe some term here, but we will quickly work on 0, 1. So here the digits are positive integers, and what is particularly convenient is that if we take the so-called convergence, which correspond to the beginning of such expansions, these rational approximations of alpha converge quickly toward alpha. That is to say, for all n, we have this convergence. So these are interesting tools. These are interesting things that provide continued fractions, good approximations of real numbers. So what I'm going to do here is first to recall how we prove such convergence property. So I still have in mind that we will want to extend this to the higher dimensional framework. So that's useful to see how we prove such properties. And we will focus on ergodic issues, and in particular on the invariant measure. So that's what we want to do with the one-dimensional framework. And since we have in mind a matricial extension, we'll try to present things as much as possible under matricial terms and dynamical terms, which leads me in a natural way to introduce the Gauss map, which is the map which runs from 0, 1 to itself, and which associates to a number x the fractional part of 1 over x, that is to say 1 over x minus its integral part, and which maps 0 to 0. So that's a Gauss map. So we have a dynamical system. For the moment, we don't have a measure theoretic dynamical system, but we have at least a topological dynamical system. We have something which acts on a compact space. And so just to see the connection with continued fractions, if A1 is equal to 1 over, to the integral part of 1 over x, what we have is that T of x equal 1 minus x over 1 over x minus A1. That is to say, x is equal to 1 over A1 plus T of x. So we've started the process of getting continued fractions, and if we continue with T of x, we've got something like that, etc. So T of x is something which is smaller than 1. So we have something which is non-negative, a positive integer, plus something smaller than 1. So here, from now on, I will forget about the A0, which is a minor detail in the picture. So we want to have a matricial viewpoint. Okay, so we can already write things under matricial form, just by making this remark that we have this way of writing things, which is the following. X is equal to this, so that can be written like that. But if I am more carefully, I'm thinking here in terms of in projective terms. But if I write exactly what happens, I have to renormalize. So to be more correct, I have to multiply by this scalar. So we have a matrix times something which implies the first step of my dynamical system, and a matrix that I have created. I write it again. I will have x, t of x, t n minus 1 of x, a1, 1, 0, an, 1, 1, 0, 1, tn of x. I just have linearized what was written here. But already this can give us a lot of information. For instance, so here I put a 0 that will correspond to the expansion 1 over a1 plus 1 over an. To be more precise, here I have considered this step of my expansion. But if I replace Tn of x here by a 0, I will get my truncated expansion, and then this will give me Pn over Qn defined here. So this is what I will do. So I've got my product of matrices. And I will forget about my renormalization terms, what I'm interested in vectors. So by renormalization terms, I mean x t of x, tn minus 1 of x. I just look at my product of matrices. And I apply it to 1, 0. What I claim is that it will give me the first, so that gives the first column of this product of matrices. It will give me my convergence Pn over Qn defined as this truncated expansion. So what I claim is that this matrix, that I will call Mn, has for first column Pn over Qn. This truncated expansion. And then it's not difficult to check that the second column will be also connected to the convergence. Pn minus 1, Qn minus 1. So now I've found my convergent in this matrix that I've obtained by iterating my algorithm. And for free, what I get is some classical relation which gives that the determinant of this matrix is equal to 1 in absolute value, because the determinant of each of these matrices is equal to 1. That means that Pn and Qn are coprime, so I don't have to care very much when I give such a definition of Pn over Qn. And I will need some more relation. So maybe I will try to keep on this blackboard all I've got so far and all I need. So far, I will have this relation on the determinant. What I'm interested in is also in this relation that we will get immediately. So for all t strictly positive, we will have this formula. And I will use the notation that I will write here. This notation corresponds to the beginning of the continued fraction. So on the brackets, I write the beginning of the continued fraction. So what I claim is that I got also this relation. Well, to get it, I just do it here with an plus t and 0. So, and if you make the computation, knowing that the product until n is Pn Qn, you just get this relation. So knowing that the matrix without t is equal, the first column is equal to Pn, and then you add a plus t here in the coefficient. So you get this relation also very easily from this linear viewpoint. And now we have all what we need to get convergence properties and ergodic properties. So this is what we will do now. So we will keep this in mind, these two properties. And we will now prove convergence. So we will prove the relation which is above here. So I stress the fact that if we already think to a multidimensional case, we won't work with 2 by 2 matrices, but with d times d matrices, and we will make the same kind of rules. We'll start with rules like t of x, which is connected to what Pierre told you this morning, a Euclid algorithm. You subtract a number to another one. So this is what is done here via some renormalization, but the inverse of this matrix here, if I consider the matrix A 1, 1, 0, its inverse is just this matrix, and the A is maybe not a good choice. If I apply it to a vector AB, that corresponds exactly to Euclid algorithm, which consisted in subtracting one vector to one entry to another entry. So this is how we will get our generalizations. We will generalize this kind of operations, generalizing this kind of matrices. We will have such products of matrices, such convergence, and we will try to get the same kind of information. So I want to prove the convergence of the algorithm. That is to say, I want to prove this relation, alpha x minus Pn over Qn is smaller than 1 over Qn square. So I will just use what I have here. So x is equal to 1 over a1 plus 1 over a2 plus an plus Tn of x. So I've got a convenient expression for this. So I just have to make the subtraction between x under this form minus Pn over Qn. And what I will get is the two denominators will occur. And the numerator will have the nice property of when you reduce, of giving you 1, if I'm not mistaken in my computation. Yes, the determinant property. But maybe I should do the computation. I think I've got a Tn of x. It's just I'm lazy to do it, but yes, a Tn of x. So it's just putting everything on the same denominator, and we get this. And so I claim now that I have everything what I need, because I will write this like that. And I've got information on 1 over Tn of x. Because I know that 1 over Tn of x is a n plus 1, just by iteration of my algorithm. So that gives that 1 over Tn of x is between a n plus 1 and a n plus 1 plus 1. So now I can get an upper bound and a lower bound for this quantity. So it will be smaller than 1 over Qn in both directions. So here it will be smaller than an plus 1 Qn plus minus 1, which gives you a Qn plus 1. And it will be larger than a Qn plus Qn minus 1. Plus Qn plus 1, sorry. Well, what we want, anyway, is x minus Pn over Qn is smaller than 1 over Qn squared for all n. So I've given the details here because we will use them later for having good estimates on the growth ratio of this kind of quantities, which measures the quality of approximation. But for our purposes, we just needed this. So this is very comfortable because if I multiply by Qn, it's not only that x minus Pn over Qn is smaller than 1 over Qn. We also have this. So that can be considered as a weak convergence property, but here is a strong convergence property. When you renormalize by Qn, you still have something which tends to 0. So since you told me that you knew about continued fractions, and maybe I haven't recalled everything, the sequence of Qn tends to infinity. So here we have something which tends to 0 and exponentially fast. So we have obtained a very good quality of approximation, and we will see in the higher dimensions that if we can get hope for something like that, we won't be able to have such a good quality of approximation. For those who know Dirichlet's theorem, in dimension d, we will expect 1 plus 1 over d exponent, and we won't be able, in fact, with the continued fractions I will introduce in these lectures, we won't be able to attain this bound, so we won't be able to have something as good as that. So, okay, so we have convergence. Just in my, here I will, well, it won't stand very long, since my blackboard will come fall down, so maybe I will write it in the next blackboard. So I just want to have in mind that 1 over A1 plus 1 over A2 plus AN plus T is equal to Pn plus T Pn minus 1 over Qn plus T Qn minus 1. And also in my convergence proof, I've used the formulas, the relations, the recurrence relation formulas between the sequences, my denominators and numerators, which are the following. So we have these relations. and with initializations given by the following. And you get them, these relations, with the matrices that we have used. So all the usual relations you get in continued fractions have been produced just by this matricial viewpoint. So the induction relations, the induction proofs we have usually when you look at these objects are found in the matricial structure. And since I'm recalling basic facts here, just for the bibliography, if you want an ergodic viewpoint, so for the continued fractions, Kinchin is definitely one of the more interesting references. But if you want to have an ergodic viewpoint, you have the Billingsley, which is ergodic theory and information. Of course, Hardy and Wright for the starting points, and also I recommend the Dajani Kreikamp book. But you maybe say a few words on this, which is the ergodic theory for numbers. So that's only for continued fractions, usual continued fractions. Then in the next lectures, I will give you more references for.
There's also Perron. It's in German, but it's in 2 volumes. It's very exhaustive.
Sorry?
Perron.
Oh, yes. Kettenbruch. Sorry? You? Okay. But here I'm on the one-dimensional framework. Later we'll give more references for the higher dimensional one. So far we have our Gauss map, convergence, linear algebra viewpoint, and we haven't discussed for the moment of invariant measures and ergodic theory, so now we're going to enter this topic. So you've heard about ergodic theory yesterday, invariant measures. So what we're looking here now, what we're looking for now is to find an invariant measure. So the first question we can ask is whether the Lebesgue measure is invariant for this transformation. And we will see that it is not. And just to have the measure theoretical setup, just to precise the idea, we will work with 0, 1. And of the Borel sets. For the Lebesgue measure, I will use a notation, we have T, and the Lebesgue measure. For the Lebesgue measure, I will use the notation M. And the question I have is, what are there invariant measures? What are there? Are there some nice invariant measures with respect to the Lebesgue measure? So I remember that an invariant measure with respect to the Gauss map, it's a probability measure mu, such that for every Borel set, we have this property. T is highly non-injective. In fact, if we look at its graph, well, it's something which works like this. So we have some fundamental intervals, 1 over k plus 1, 1 over k, on which the map, the restriction of this map on this interval is 1 over x minus k. And then we have here, towards 0, some closer and closer hyperbolas. So here is the graph of the Gauss map, and we recognize here, if we put 1/2, the second half of the map that Pierre gave yesterday, this morning, which was the Farey map, which corresponds to the additive process of finding the Gauss map. So the Gauss map is a multiplicative version on a process which corresponds to what Pierre showed, which not exactly what I wanted to say, but okay, so yes, exactly, yes, 1/2. So on 1/2 you find this branch. So this is a multiplicative version of an additive process, but we will come back to this kind of ideas later. So we want to find an invariant measure, and it's not difficult to check that the Lebesgue measure is not invariant. So what kind of invariant measures can we find? For instance, if we take the golden mean, the golden mean between 0 and 1. We know that it's a fixed point under the Gauss map. Well, okay, if you take the Dirac probability measure at rho, well, it is invariant. Okay, but we are not completely satisfied with such an invariant measure. Dirac is not very, does not say very much about this transformation. If you take now some point n such that is fixed by the Gauss map, and there exist such points, okay, take the Dirac at this, take the sum of Dirac at these points, so maybe so this measure is also T-invariant. But it doesn't cover much of the space. If you remember what ergodicity means, you want to understand how the orbits behave, you want to see whether the orbits are dense, whether they are equidistributed. So we know that not all orbits are dense, just look at the golden ratio. But as Pierre said this morning, we don't care about sets of zero measure. So we are looking for an almost everywhere behavior. Almost everywhere, a priori with respect to the Lebesgue measure, because we started with the Lebesgue measure on the set 0, 1. Okay, so we find invariant measures, but they are not very they are singular with respect to Lebesgue. This is not exactly what we are expecting. And if you take, so since also the set of measures is metrizable and compact, we can take an accumulation point for the weak star topology of such things for an infinite orbit. So this is not very effective. It doesn't say much with respect to measures. But anyway, if you want to make computer experiments to see how orbits distribute, that's an effective way that can be used. And for instance, Sébastien Labbé here uses that to guess invariant measures for multidimensional continued fraction algorithms. Okay, so that's the picture. So I don't know whether yesterday you mentioned about ergodic measures. I mean, when you take two ergodic measures, they are mutually singular. Or... Okay, so you'll know. So I won't spoil you what you're going to say. But so Karma is going to explain you tomorrow that if you take two ergodic measures, then if they are probability measures, either they coincide or they are mutually singular. And if you take a measure which is absolutely continuous, two ergodic measures, one is absolutely continuous with respect to the other one. What do I want to say?
One is ergodic, the other is absolutely continuous.
Exactly. Then they
Also the same, if they're absolutely continuous.
they coincide. So what I wanted to say is that you will often see a sentence saying the Gauss map, the Gauss measure that I will introduce. The Gauss measure is the invariant measure of the Gauss map. And the Gauss measure is defined as follows. It's a measure which is absolutely continuous with respect to the Lebesgue measure and which has this density 1 over 1 plus x, so mu of b. And we have a renormalization parameter to make it a probability measure. So that the measure here, it's underlying the Lebesgue measure. It's defined for every Borel set, like that. So it's the measure, the absolutely continuous measure with respect to Lebesgue, which has density function 1 over log 2, 1 over 1 plus x. So that's the Gauss measure. So when you see this sentence, the Gauss measure is the invariant measure of the Gauss map, what is meant is it's not the only invariant measure. We have seen a lot of them via Dirac. So it's the unique invariant measure that is ergodic and absolutely continuous. So this is something you find often for maps of the interval. So this sentence means the following. The Gauss measure is ergodic. And so corollary. It is the unique, absolutely continuous, so with respect to Lebesgue, measure that is T-invariant. So it's T-ergodic and, I'm too fast, and T-invariant with respect to the Gauss map. So it's a particular measure. So what I said before is you have a lot of invariant measures, but there are some invariant measures which tell you more than other ones with respect to the object we start from. We start from a transformation of the interval. It's more comfortable to have something connected to the Lebesgue measure. So that is to say that forget sets of zero measure, which correspond to the sets of zero measure you don't see with the Lebesgue measure. So it's a reasonable picture. You have an absolutely continuous measure with a quite simple density, which is T-invariant ergodic, and it's the unique measure that satisfies these things, thanks to what you will see tomorrow through Karma's lecture. When you have two ergodic measures and one is absolutely continuous with respect to the other one, they coincide. So if you had another absolutely continuous measure with respect to this measure, they would coincide. And here, absolutely continuous with respect to the Lebesgue So when I will say things like almost everywhere, it's with respect to this measure, which will be our measure now, or with respect to Lebesgue measure, they have the same set of 0 measure. So I've got now 2 things to prove. The T invariance. Well, this will be easy because I know my measure. It's just, we will just have to make some computation. The difficult part is to guess this measure. And to prove ergodicity, and we will see also that it's not too difficult. So for what will come next in the multidimensional setting, in a paradoxical way, convergence is often more difficult to get than guess. So we can have convergence problems and having a nice ergodic framework or knowing invariant measures. Okay, so now I want to do the invariance and the ergodicity, and then we will be done with the one-dimensional case. So the T invariance. So first we will make some remarks. We will work. We have seen that there are some intervals which play a certain role. The intervals 1 over k plus 1, 1 over k. These are, as I said, the fundamental cylinders of rank 1. If you have seen this vocabulary of cylinders. Not yet. Okay, so well. I will introduce what I call fundamental domains and fundamental intervals. So I will use the notation C like cylinder. I really have in mind what happens in symbolic dynamics when we look at sequences which start with a given prefix. So here, I look at real numbers, whose continued fraction starts with a given beginning. So here, A1 are digits. So these are positive integers. They are fixed. So this interval corresponds to the elements in 0, 1, such that x 1 over Tn minus 1 of x is equal to ak for k equals 1 to n. I just mean here the real numbers whose continued fractions start with these digits which are fixed. So this is fixed, and then you do what you want. So this is what I mean here. Also, it's not very clear since I've used this notation before for other signification. So if you look at A1, CA1 is just 1 over A1 A1 plus 1, 1 over A1. As a warm-up, just we want to know when 1 over x is between A1 and A1 plus 1, and this is just what it means. X belongs to this set. So what is nice here is that these intervals, which are smaller and smaller, we will see, we will look at their size, generate the Borel sets. So this is something we will have often in continued fractions. So we will be able, when we will have to prove things, we will be able to work with these intervals to deduce things for general Borel sets. So the fundamental intervals generate the sigma algebra of the Borel sets. Intuitively, you can think that their length is converging geometrically fast to 0, or you can think also that their bounds are rational numbers which are dense, so you can easily see that you can approximate any interval through such fundamental intervals. Also, just to be more precise concerning their size, I will introduce a function, psi, which is the inverse branch of the continuous fraction. That is to say, I consider only one step of continuous fraction, 1 over x minus 1 over x. But I take the inverse of this branch and I take n steps of this. So I will consider this map. And we have seen, thanks to this formula over there, that this has a nice expression. We can manage it. So we can give an explicit expression of a cylinder. So it's equal to psi a1 an of 0, psi a1 an of 1. And now I will have to be careful to take care of the fact that n is even or odd, because this function is growing or is increasing or decreasing according to the fact that n is even or not. You can see it because t is at the first time at the denominator, but then at another state of denominator, so you can see it like that. It comes also from this thing that if you look at continuous fraction, they alternate around the point x we consider. So that's the situation if n is odd. And if n is even, that's the converse. So if n is odd, Pn plus t, Pn minus 1 is located here. And if t grows, then you can see how the map grows with respect to the location of Pn minus 1 and Pn over Qn. And you have the converse if n is even. So so we are in the case here where n is even. Can you see something on the blackboard, or do I have to erase more? Is it readable for the moment, or? Okay. So now I can give the exact formula. So if n is even, we have Pn over Qn, Pn plus Pn minus 1 over Qn plus Qn minus 1. Okay, so we have these cylinders, and then we have got an exact expression of their length, and we can feel once again that it will be in 1 over Qn, the products of denominators, and things will work nicely on a numerator. So the Lebesgue measure of CA1 AN is equal to one over Qn plus Qn minus 1. So this shows how fast it converges geometrically to 0. And if we want, so I'm preparing the picture, the setup for the multidimensional case. If I introduce this map, which is the derivative of psi with respect to t, well, it's equal to 1 over Qn plus t Qn minus 1 to the square. So the derivative of the inverse branch with respect to t. So we will have this quantity which will come into the picture in the multidimensional case that will correspond to the Jacobian of the matrices which are behind. So we have a nice expression of this, and the measure corresponds just to the integration on of this. So we don't technically need this for the moment, but just let's have in mind what we are using to get results. So so far we have fundamental intervals that generate our Borel sigma algebra with smaller and smaller sets, and we even have something which is nice. We have what is called topological convergence. Which is that if I take the intersection of the fundamental intervals cylinders which correspond to some x, then it's reduced to x. So here in this notation, so far I haven't included in the notation A1 in the digits the dependence with respect to x, in order to have a notation not too heavy. But in all what I'm making, when I write x under this form, the digits, the AI, depend on x. So this is why what I have written here, I take the intersection of the domains, the intervals which correspond to the expansion of x, and I take larger and larger prefixes of this expansion. What I claim is that the convergence implies that it's reduced to x. So that's the topological convergence. This is something in this dynamical viewpoint which is interesting. So we have seen two types of convergence. A convergence which is natural, which was that the partial quotients tend to x, and a topological notion. And a remark, the convergence that I will call arithmetic implies topological That is to say, if I've got two real numbers that have the same continued fraction that gives you the same digits in the continued fraction expansions, then they coincide. So this seems like a tautology, maybe here, but that's a question that will be natural when we were given a way of expanding numbers. You will get digits, you will get such kind of cylinders, some kind of fundamental domains, and the question is whether points have multiple expansions or not. Okay, so now I arrive to the proof of the fact that the measure is invariant. Yeah, this was not very clever. So maybe, thank you, Karma, for just a break. So I think I can go here. So the easy part is to check that now the measure mu, which corresponds to 1 over log 2 dx over 1 over x. So mu is T invariant. So it's sufficient to work on intervals 0x. So we want to prove that for every Borel set, mu of t minus b is equal mu of b. What I say is I will work with intervals, and then it will be sufficient to get to reach every Borel set. So now I have to compare mu of t minus 1 of 0x and mu of 0x. So mu of 0x is simply the integral so let's call it y. So it's 1 over log 2 ln of 1 plus y. By the way, just a remark. If I'm asking the question to understand, instead of taking backwards orbit, I take forward orbit in the sense that I'm looking at t of 0y. T of 0y is equal to 0, 1. So it's not very interesting. As soon as you make one step, everything is possible, in fact. So it's just to remark, this is why it's not you might ask the question why we always go backwards. This has really a meaning. We want to see where we come from and not where we are going, because at each step, in some sense, we are starting from scratch. When we make one step, it's as if we started from a random number. But we want to understand what has happened in the past. So t minus 1 of 0y is equal to the union for digits possible which are larger than 1 on 1 over k plus 1, 1 over k plus y. It's just that exactly the computation we've made before. You want to know what was the digit before 0y. And so now we have to take the measure of this. So mu of this so I've got a 1 over log 2 . So this will be equal to a log of, and just for consistency, my logarithm are always the same, ln equals log. So it's a log of k plus y plus 1 and I forgot a 1 over k plus 1, 1 over k plus 1. So it's a log of 1 over k plus y minus log of 1 over k plus 1. And then thank you. Thank you. And then it's just k plus y plus 1 over k plus y, k plus k plus 1, yes, and k plus 2. And then I will modify my product. And everything works well. It will gives me log of, so I use this, 1 plus yes. Yeah, I made some.
No, I think that's
yeah.
fine because this is just one term, and then when you put all the unions, the other ones, they start cancelling.
Yeah, they start. But do you see the cancelling here?
Not at this point, but because it's just one term.
You saw already the cancelling here? No, we need this step.
I think this is fine, and now, but this is one term, and then when you do the union, you know, the sum becomes a product.
Yeah, exactly. Yeah, and then it's supposed to cancel. So you see the cancellings here?
Not now.
Okay.
But when you do the T inverse, the whole thing,
yeah.
then you will get 1 over log 2 log of the product.
Yeah, exactly, yes. Yeah, that's what I'm trying to create the cancelling, just to that we see the cancelling.
Okay, yeah.
But it's not that obvious. So I'm just... Well, anyway, I had some already here. I was too fast. I just wanted to check how you followed, and then it will. I think it will help. Thank you. K plus y. So it will be, I think, more comfortable with the ones. And k plus 1 over k. And then I here k plus 1 plus minus a log of well, I'm sure you will be able to finish. Just knowing it's a cross and it's too hot, too warm to finish it. So that's the completely easy part. It's just a simple computation, and you will find here. Then by summing, you will be able to find the right thing. So there's no, in fact, no ID hidden here. Just this trick here to find, as Karma said, the decomposition. But what I wanted to stress on was the ergodicity. T is ergodic. with respect to mu. That is to say, I want to prove that if t minus 1 of b is equal to b, if b is invariant, so for a Borel a set of the sigma Borel sigma algebra, a Borel set. So if we are invariant, then the measure of b is equal to 0 or 1. So that's what I would like to do now. Just to see that it's not, to see what we need. And that we will keep this kind of information for our multidimensional generalizations. So the proof the idea is the following. We will first work with our fundamental intervals. And so for any set, Borel set, we will first prove something concerning the Lebesgue measure. We will try to compare this measure with respect to the measure of A. So if I write this, it has no meaning because I have to renormalize. So I have to consider something like that. So that will be a computation. I will compare this, and here I will have two constants. So what is important is to have something which doesn't depend on n, which allows one to compare that's a conditional probability, knowing that you are this beginning, A1, A1, An, you know you want to compare the measure of t minus n of A with respect to the measure of A. For the moment, M is the Lebesgue measure. So that's the first step. So that will be an easy computation where the features of the algorithm is hidden. It's really a question of length of intervals, things like that. Then I will be able to do this for the Gauss measure. Because of the fact that the Gauss measure is absolutely continuous with respect to the Lebesgue measure. So if you are able to compare things implying this measure, you can do it with mu. So we will have this. We will compare it once again with respect to mu. So we divide by mu. And here the constant, well, we don't care, but just this. So that's a computation that involving the map psi that can be easily done. This just comes from the expression of mu, because you can give an upper bound on 1 over 1 plus x. That's where the 2 comes from. So this is not difficult. And now I claim that we can conclude with this. So take our invariant set. So here I can replace t minus n by, I can forget about this. So I've got something which tells you that the measure of A intersected with a fundamental interval is to be compared with the measure of this interval, mu of A. And I will also assume that the measure of A is strictly positive. So now, since I've been able to do it for every fundamental domain, and fundamental domains, the class, the monotone class generated by fundamental domains generate the Borel set, the sigma algebra, then we can say that this holds true also for every other Borel set. but we have something very strong, which is, I don't know whether you've already spoken of mixing properties, but it's really, okay, so something you'll see in the flavor of kind of mixing. We are very close to ergodicity now. Just take for B the complement of A, and then you get a contradiction. So, because here we have supposed mu of A strictly positive. So if we suppose mu of A is strictly between 0 and 1, you get a contradiction, and you want to prove either options. So the proof is a computation here, just a consequence of the absolute continuity, and then a classical argument. And this is this is a classical way of making proofs. And this is something you will find under the idea of Knopf's lemma in Karma's lecture. So this is a process completely classical. Since we're all tired, I won't prove this, and I will come back to this. I will come back to this idea because hidden it's a condition that we will find, which is Renyi's condition, so we'll do it later. But just in the minutes that I still have, I would like to prepare the background for multidimensional continuous fractions, just to give you an idea of what can work and what can fail when we go to the higher dimensional case. So I want now to go to the multidimensional case, and I want to make devices generalizing the Gauss map. So how can I do that? Well, I will use this idea that Pierre said this morning. The Gauss map is just subtracting one number to another one. So to have other generalizations, I will start with two numbers, x, y. But then, instead of starting with two numbers, I will start with, in fact, three numbers, because for continued fraction, x corresponds to subtracting b to a. If I will not work in the projective space. I will work in the linear space now. So I want to find rules generalizing this. So I start with three numbers. I would like to generalize Euclid algorithm. So what can I do? I can make subtractions. So I suppose I take three numbers, positive numbers. And I will ask the question, for instance, if I want to make a computation of a GCD, if these are non-negative integers, I will ask the question, what kind of rules can I have to make these numbers decrease if they are integers, or what kind of rules can I make if they are real numbers to get nice rational approximations. And then I will make several propositions, and all these propositions will have names and are well studied. So maybe I will start with more natural ones. Well, you'll see whether we find this natural. For instance, Selmer rule, Selmer algorithm consists in subtracting the smallest entry to the largest. Well, if you want, if you have three positive integers and you want to compute the PGCD, you can think it's quite natural to try to make the numbers decrease as fast as possible. So that's Selmer. Brun will consist in subtracting the second largest to the largest. So for the moment, for today, I won't give you the full zoology of possible algorithms, and I won't give them an expression in the flavor of this. Just for the moment, I want to make you feel the problems we can have even with these simple rules. So, and what we want to study is convergence, invariant measures, ergodicity, and things like that. So start with Selmer. And start with 1 over phi square, 1 over phi and 1000 with this rule. So I subtract the smallest to the largest. And then I will reorder things. So the smallest is 1 over phi, knowing that for phi now is equal to the golden ratio. So it's not exactly the phi we have previously, but the value which is larger than 1. So okay, what I do this. So I've got something which is modified by this entry. And then if I subtract this, I enter with, if I put the smallest first, I will find this. It's just because of this rule. So divide, so 1 over phi minus 1 over phi square is equal to 1 over phi 3. And I continue. And then I see that I will continue to play with my two first entries. Phi k, and something which is modified, but in very marginal way. This series is convergent. Okay, so if I continue, this tends to 0, 0, and some constant, which is strictly positive. So if you have two entries, here you're making continued fractions. Yes?
Isn't Selmer supposing the smallest one only to the largest one?
Sorry?
So is Selmer algorithm
Yes?
substitute the smallest one to only the largest one?
Yes.
So it doesn't modify the middle one?
No, Poincaré is the smallest to the...
But you speak about Selmer?
Yes. So Selmer
It
is...
should not modify the middle one. This is Poincaré.
Poincaré is the smallest to the middle and middle. Smallest. Oh, sorry. Yes, you're right. Sorry. Yes. Yes, 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 yes. Exactly. Poincaré fully subtractive. Thank you. I'm tired. So, fully subtractive. Subtract the smallest to all the largest one. So I subtract this one to this one, and this one to this one, which is, I hope, what I've done. And then, so thank you very much. And so what happens here is that if we had only played with the two first entries, we would have something which goes to 0. That's not a big issue. You reduce things, but things go to the same rhythm towards 0. And here you have something which on the coordinate tends to something which is strictly positive, and on the two other coordinates to something which is equal to 0. So I will stop just with this idea. So we will see what it means, in fact, what kind of problems it creates, how, so we will ask the question, can we consider it's a good algorithm? Does it converge? What can be said about ergodicity? With the algorithm, which does not behave in the same way on all coordinates, contrarily to what Euclid does. I'm going to stop here.